Hello everyone, my name is Raina DeJute and welcome to my LeetCode problem solving video. In this video we will be going over 5 LeetCode problems and explaining not just what the solution is but the underlying logic behind it. So without further ado, let's get into our first problem. So the first problem we have is customers who never order, and before we get into any solution, we notice that this looks a little bit different from JavaScript, and that's because it's in MySQL. So before this problem, I had zero experience with MySQL, so my understanding is still a little bit surface level, but we're going to try to explain it the best way I can. So we see in this description we have two tables. We have customers and then we have orders. So basically the problem here is looking for missing relationships. So we want everything in customers, but only if it doesn't exist in orders. In this problem, we are using what's called a left join approach. So we join the customers into the orders and we keep all customers. And the key trick here is this null. If there's no match, then the order fields become null. So what this line is saying is show me the rows that failed to match. So the first problem that we can start with is the group anagrams. So the objective of this problem is that we are given an array of strings and we need to group all the strings that are anagrams of each other. So the output should be a list of groups where each string contains words that share the same characters but in different orders. We are not comparing every string directly, we are trying to efficiently identify the equivalence groups. So instead of comparing strings pair by pair, we transform each string into a canonical representation, which just means a sorted version of itself. All anagrams map to the same canonical key, which allows us to group them using a hash map. So as you can see, this is the solution here. It has been solved, so let's break this down. So at the very top, this from collections import default dict. We import this default so we can automatically create lists for new keys. So this removes the need for manual existence checks when we are grouping values. Then we have this class solution. This is required by LeetCode. The platform instantiates this class and calls the method internally. So this is just a structural wrapper and not really part of the algorithm itself. Then we have this line right here. This just defines the entry point of the solution. So this strs is the input list of the strings we are grouping, as we can see here. And then we have this line right here. This is the core grouping structure. So each key will represent a canonical form of a word, and each value will be a list of words that match that form. So this is effectively our grouping container. And then we iterate through each string individually and assign it to a group. Each iteration processes one word. And this is the key transformation step. So we sort each string so that all anagrams produce the same output. So for instance, EAT and ATE end up both being AET. This creates a shared identifier for equivalent strings, aka anagrams. And then this line, we group the original word under its canonical key. So we preserve the original data but organize it using this transformed structure. And then we return only the grouped lists. The keys are no longer needed once that grouping is complete. So this is what is called a canonicalization and hashing problem. We convert complex comparisons into simple key-based grouping by normalizing the input first. Our next problem is this duplicate emails, and again, as you can see, it's solved and this is the solution. So the objective of this problem is we are given a table of emails and we need to return only the emails that appear more than once. So the goal is to identify duplicates based on frequency, not individual rows. So the strategy here is we group rows by email, then we count how many rows exist in each group. After grouping, we filter based on group size using what's called halving, which is right here. So this select email is we are returning the email column as the final output. This is just defining what it is that we want to display. And then from person is we define the base data set that everything operates on. And then we have group by email. This transforms row level data into grouped buckets by email. So each unique email becomes one group. And then we filter based on group size. So we only keep groups where the email appears more than once. This is filtering on aggregated data, which is why having is required instead of where. So the main idea for this problem is it's a group aggregation filtering problem. We restructure the data first, and then we evaluate the group level conditions. On to our next problem, which is combine two tables. So the objective objective of this is to combine two tables, the person and the address. So we need to return all people and attach address data if it exists. If a person doesn't have an address, then we still include them, but we put null values. So the strategy here is to use a left join to preserve all the rows from the person table while optionally attaching matching address data. So starting from the top, this from person P is our base data set. We want to preserve every person. We alias it P for clarity. Then this left join is we attach the address data, but do not exclude people who lack addresses. So person is still fully preserved. And then this line defines how rows match between tables. It doesn't filter, it establishes relationship mapping. So the core takeaway for this problem is it is a data preservation join problem. Join types determines whether missing relationships are preserved, which is a left join, or discarded, which is an inner join. And then our next problem is employees earning more than their managers. So the objective of this problem is that we are given a table where employees reference their managers in the same table. We need to find employees whose salary is greater than their manager's salary. So we are comparing related rows inside of a single data set. The strategy here is to perform a self-join, so we can treat the same table as two logical rows, employee and manager. Then we compare their attributes. So this from employee E is we define the employee perspective. This is one role in the comparison. Then this join employee M, we join the table itself to represent managers as a separate logical instance. So now we have two views of the same data set. And then we connect the employee to their corresponding managers. This builds the relationship between the rows. Then where E salary is greater than M salary is we compare attributes across the relationship. So we only keep cases where the employee earns more than the manager. So the core takeaway from this problem is it is a self-referential hierarchy problem. We model parent-child relationships within a single data set using self-joins. And then finally, we have our last problem, which is customers who never order. So the objective here is that we are given customers and orders. We need to return customers who have never placed an order. So we are identifying missing relationships between two data sets. So the strategy here is that we use this left join to preserve all of the customers and then filter for those with no matching orders using null. So breaking this code down, this from customers C is showing that customers is our base data set. So we evaluate every single customer. Then left join is we attach orders when they exist, but don't remove customers without orders. And then this line defines how customers maps to orders. And if no match exists, then the join fields are returned null. So this condition isolates customers with no orders. And this is what is called an anti-join problem. So we're not finding matches, we are explicitly finding not matches using null behavior from left join. So to recap the 5 problems, number 1, the group anagrams is canonicalization. It converts inputs into a shared identity, so grouping becomes trivial. Then our second problem is aggregation, or the duplicate emails. We transform row data into groups, then we evaluate group properties. Then we have relational modeling, or join. So we choose a join type based on whether we preserve or filter data relationships. Then the hierarchical modeling, or the self-join. We represent parent-child relationships with a single data set. And then finally, our anti-join logic, or missing relationships, using the left join plus null filtering to find out what doesn't exist. So I hope that made sense. Thank you for watching, and I will see you on the next one.